Moving on to the next question involving a horizontal circular motion from a conical pendulum. We have a more general question. So it talks about the pendulum. We'll draw it out. Okay, so we have a pendulum, light and extensible string from point P. The object has a mass of m, so therefore there's a weight of mg. It describes a horizontal circle with center O, where O is a distance h vertically below P. So straight away we can now say that this distance here vertically is h. We are told that omega is the angular velocity, and we're asked to show that omega squared is equal to g over h. And then we're asked to find an expression for the period of the conical pendulum in terms of h. So it feels as though you haven't got much to work on there, okay? But we can appreciate that there's a radius, okay? We've got the length of the string, neither of which we know. Now, that string has a tension, and again, the components of it are t cos theta, where theta is that angle, and we have t sine theta, which is the force acting towards the center of the circular motion. So to some extent what we need to do is we need to try and get a sense of what t is, or maybe explain t as an expression. Also, we may want to get something involving r. So let's just work this through. Let's first work through the vertical components. So we know that with the vertical components that t cos theta is equal to mg. So similar to the last question, so t is equal to mg divided by the cos of theta. Now, meanwhile, if we want to describe r, we can do that in terms of h. Where we appreciate the opposite over tangent TOA, opposite over adjacent, sorry, we have a situation where the opposite is going to be the adjacent multiplied by the tangent of the angle. So we then have a situation where the horizontal forces, the centripetal force, we appreciate that that centripetal force is t sine theta. The mass is the mass. The radius, well, we've got an expression for the radius. It's h tan theta. And we don't know what omega squared is. We have an expression for t, so I can actually add that one in. So mg cos theta multiplied by sine theta. Immediately, alarm bell should really ring there as to what's going to be going on there, because you're supposed to know that sine over cos is tan. So we end up with mg tan theta on the left, mh tan theta omega squared. We can cancel out the m's, we can cancel out the tan theta, and we're left with g is equal to h multiplied by omega squared, and we divide by h, and we get our required expression. Omega squared is equal to g over h. Now, just very quickly, one of the things, why did I choose this formula? Well, since I was being asked to get omega squared, it's not surprising that actually I'm going to use one of my formulas from my original sheet that has omega squared in it. I'm not going to use mv squared over r, for example, which is the other formula that I can use for the centripetal force. Okay, so you're following your nose a little bit in terms of what you're going to use. The last part of the question was to hence find an expression for the period of the conical pendulum in terms of h. So again, using our formulas that we have available to us, we have the fact that a period, now t is in terms of the period as opposed to the tension, it's 2 pi over omega. Okay, it's in the sheet that I gave you. So all I need to do is substitute an expression for W into that. Now, so if I do that, hang on a second, I have to appreciate that omega is the square root of G over H. So the reciprocal of that, I suppose 1 over W, 1 over omega will be the reciprocal of that square root. So we can say straight away 2 pi and then H over G. You can go through a slightly more long-winded process of saying 2 pi divided by the square root of G over H, and there's various different ways you can argue about how you manipulate that expression to eventually get the answer, okay, which is 2 pi square root of H over G. Moving on to the third question of 4 questions I'm going to be looking at. Question 13 on your sheet. This is a scenario where you have that conical pendulum motion, but it's actually that the particle is just resting on a table as it's being hung from above, but it's actually on a table. So the particle describes a horizontal circle of radius 30 centimeters on a smooth surface of a horizontal table. So smooth, therefore there's no friction in this instance. We'll look at friction in another lesson. Okay, with the center of the circle being a distance of 72 centimeters vertically below P. Angular velocity is 2 rads per second. So the first thing we do is we draw our forces, the components of our forces, and we have this tension on the string. We can break that then down into the horizontal and vertical components, and to some extent we can actually now ignore that tension. I suppose I'll tell you what we'll do. We'll just draw it in a little bit more lightly as such. There's a tension. Anyway, so we've got t cos theta and t sine theta in the vertical and horizontal directions. We've got 3g vertically down. I've put in red there the measurements. The radius of the circle being described is 30 centimeters. I'm writing my measurements in standard SI units, which is meters. The distance above the table above the center of the circle has been described. The point of the string is 72 centimeters above it, so 0.72 meters. We know our angular velocity is given as 2. That's all the information we have. Now the only extra thing I have to add into this diagram is the fact that in addition to these forces here, we also have a normal reaction. So the normal reaction is what the table effectively is creating. The object that's being spun around effectively is just skimming across it, but at the end of the day, the table is still contributing towards the mass remaining in that horizontal plane. We don't know what theta is, and probably it'll be worth our while getting an understanding of that. So our theta is going to be, well, opposite over adjacent. It's going to be the inverse tan of 0.3 divided by 0.72. Okay. Now, when I work that through, you'll realize something fairly quickly. We actually get the inverse tan of 5 over 12. So it's actually worth sometimes you actually bunging in the ratio first, not doing the whole thing, the whole calculation, tan inverse tan 0.3 divided by 0.72, because you'll get an angle of 22.62 degrees, which won't mean much. But as soon as you realize actually that 0.3 over 0.72 is actually 5/12, again, an alarm bell should ring, and it should make you realize that if you want to work out sine theta or indeed cos theta, it is a very straightforward process. Straight away, it's a Pythagorean triple, 5, 12, 13, and we know therefore as a fact that the cos of the angle will be 12/13, and the sine of the angle will be 5/13. I've not had to do any calculations with my calculator on that one. I've just been able to do that very quickly in my head, and it's worth you realizing it. Just speeds you up a little bit. Anyway, we start by looking at the vertical forces occurring. So we have T cos theta, and we're adding on to that our normal reaction, and that's equal to mg. So we can insert a few values into that. So cos theta is 12/13, and the mass is 3, so it's 3g. Now, I don't feel there's much I can do with that at the moment, actually, because I've got two unknowns. I've got both t and r are unknown. So let's just hold fire for a second. Let's look at other things that we can do. Let's work on maybe the horizontal and see what forces are doing there. So horizontally, we have a situation where using F equals mr omega squared. Well, F is t sine theta, m is m, r is r, omega squared. We can then now substitute what we have for certain things here. So the sine of theta is 5/13, the mass is 3, the radius is 0.3, and omega is 2, so omega squared I can put into that. So when I work that through, I find my tension is basically 3.6 divided by 5/13, and I end up with 9.36 newtons. So now that I know my tension, I can now work out my normal reaction. So let's just remind ourselves, I'm being asked to work out the tension of the string. I've worked that out. I've worked out the angle. Well, actually, I suppose I should actually point out to you, I never actually worked out the angle. I suppose I should actually write that out. Okay, so it was the inverse tan of 5/12, which was 22.62 degrees. I suppose the fact that I didn't actually work that out, I don't actually need to know what the angle actually is in this instance. Anyway, I've answered the question. So the last step is now to work out the normal reaction. So now I can insert this tension back into my equation that I had for in the vertical. So if we take that, so tension, well, I suppose we can rearrange this first. So the normal reaction is going to be 3g minus the tension multiplied by 12/13. And that, when you calculate it out, it works out as 20.76 newtons. Again, the key idea here is I'm looking at it vertically and making sure that the forces up are the same as the forces down. And the second thing I'm doing is I'm looking at the centripetal force using one of the formulas, usually F equals mr omega squared, but not always. And again, looking at the forces, the horizontal component of the tension that's being created by the string is that centripetal force, and you equal it to mr omega squared and work from there. In this instance, I had to sort of work backwards a little bit. I didn't get what I wanted straight away out of the vertical. I had to go to the horizontal, get some information, and then bring it back to get the normal reaction.